body through his mouth or nose, and quickly moves to his pharynx or throat. From there, the air passes through his larynx or voice box and enters his trachea. Adam's trachea is a strong tube that contains rings of cartilage that prevent it from collapsing. Within his lungs, his trachea branches into a left and right bronchus, which further divide into smaller and smaller branches called bronchioles. The smallest bronchioles end in tiny air sacs called alveoli, which inflate during inhalation and deflate during exhalation. Gas exchange is the delivery of oxygen from the lungs to the bloodstream and the elimination of carbon dioxide from the bloodstream to the lungs. It occurs in Adam's lungs between his alveoli and a network of tiny blood vessels called capillaries. Here you see red blood cells traveling through his capillaries. The walls of the alveoli actually share a membrane with Adam's capillaries. That's how close they are. This makes it possible for oxygen and carbon dioxide to diffuse or move freely between his respiratory system and his bloodstream. Oxygen molecules attach to red blood cells, which travel back to his heart. At the same time, the carbon dioxide molecules in his alveoli are blown out of Adam's body with his next exhalation. This gas exchange allows him to replenish the oxygen he needs for his survival.
The part I particularly wanted you to notice there was the business of the alveoli, those little balloon-like sacs in your lungs where the gases are actually exchanged. Surrounding each of those is a network of blood vessels, capillaries, okay? The good stuff goes from the lung or the alveoli into the blood, and the bad stuff goes the other way. They just switch places. But they're so close together that it can actually go right through the wall of the cell, right through into the capillaries, okay? Now we understand that good stuff goes in, bad stuff comes out, but what I really want you to get today, what we're going to talk about here next, is why. Why does the air want to go from here into here? When you say you suck in air or you pull in air, what are you actually doing? And you know a little bit about this, but not the whole picture. Who can tell me what you're actually doing, head up, Matt, when you breathe in that makes the air go in, Dominique?
We're like putting oxygen.
What are you doing with your body to make air go into your lungs? Okay, well, yeah, you know pressure's going to have something to do with this because I'm going to talk about it for about 20 minutes here. But what are you actually doing to make the air go in? There you go. Did you hear what he said? You're making more space around the lungs. That's the key here. And I explained that to you yesterday. You all should know that it's making more space around the lungs. But you don't all necessarily know why that works. That's what I'm going to talk about here next. So this was the model of our lungs, and we can see that they inflate and they deflate without ever being touched directly. They don't suck in air on their own, and they don't blow air out on their own. It's the stuff around the lungs that affect that. So by pulling down on this thing, what does this represent? The diaphragm. I make more space. And the air in this room says, hey, it's less crowded. I want to get in there. And it goes in through the little opening into the balloons. Conversely, when I take this and I push the diaphragm up, I make the air that's inside this container more crowded. They're all squeezed together and they're saying, hey, we want to get out of here. It's better out here where it's less crowded. And they're trying to get out. Well, they can't get out through the balloon, so the air in the balloon gets pushed out. Does that make sense? So now we know why. It's making more or less space inside the body. And the real deal, what we're talking about is the diaphragm going down, and what happens with the chest? It expands. See, a lot of you think the chest expands because of the air going in. The truth is we expand our chest, and that makes the air go in. just like you saw here. How many think they understand that? All right. Now we're going to take it a step deeper. You know, when you ask a little kid, or a little kid asks you a question, they say, Daddy, why is the sky blue? And you say, you know, because of the way the sunlight goes through it. Why does the sunlight go through it like that? Well, because light travels in waves. Why does light travel in waves? You know what I'm talking about? They keep asking you another question and another question and another question, and you're like, I can't answer all these. We're going to dig deeper today. We're going to dig deeper as to why. Why is it that the air wants to go in there? Okay? And I've kind of answered it a little bit, but what I want you to understand about this is it has to do with pressure. And pressure is a big topic. It isn't just important in breathing. Pressure is important in weather. You're going to be a weather person, meteorologist. You're going to study pressure. If you're going to be a pilot, and you're going to learn to fly a plane, you need to know what keeps that plane up in the air. The answer is pressure. Okay? You're going to jump out of an airplane and you expect the parachute to do its job. You better understand about air and pressure. So this is a big, big concept in science. It covers a lot of different things. And I'm going to show you a number of different demonstrations here, and hopefully by the time I'm done, you'll have a good handle on it. Let's start with just looking at a simple balloon. Why? Why does this balloon not blow itself up? Why does it just sit there? It doesn't inflate itself. Okay, so he says the air, like the air in this room, doesn't have enough pressure by itself to blow it up. Okay? We'll see if that's correct or not. Not quite. Okay, you'll notice that this isn't sealed off, right? So there is air in this room. You would agree with that statement? And it has the capability of getting in there, right? Why doesn't more of it rush in there?
Because you're putting pressure.
Okay, kind of. Okay, let me ask you another question here. Am I exercising?
No. Yes.
I hear no, I hear yes.
Yes.
It's hard to tell, isn't it? If I told you that I'm pushing hard with my right hand and I'm pushing hard with my left hand, would you agree that I'm exercising?
Yes.
Yes. Okay? Doesn't look like I'm doing anything though, huh? Okay, when something happens, when the balloon gets blown up, now we can see pressure doing something. We notice pressure when there is a difference. I'll repeat that again so you can grasp it. We notice pressure when there is a difference. We notice someone exercising when we see them moving. There's a difference from where their hands were to where they are now. Oftentimes we don't even appreciate that air is doing something because it doesn't seem to be doing anything at the moment. Okay? When this balloon is just sitting here, it isn't inflated. And the reason it's not inflated, Zach, is?
Because it's not expanded.
But why? Why doesn't it inflate?
Pressure's the same on the inside and the outside.
You'll be happy today, too. Pressure's the same on the inside as it is on the outside. That's the big concept. You see, nothing remarkable happens when the pressure's the same, inside and outside. I know it's the same. You know why? Because it's open there. If air wanted to go in there, it could. Okay? The pressure is different on the inside and the outside here. Where is the pressure high? Inside. Where's the pressure low? Outside. And that leads us to our main rule about pressure. I put a ball up on a hill. That ball is going to roll downhill. Ooh, big shocker, right? It will never want to roll uphill. Gravity will make it roll downhill. It goes from high to low. Pressure is the same way. It always goes from high to low. Head up, please. So, if I take a pin and I poke a hole in it, the air will go from high pressure out to low pressure. Got it? What I would like you to picture now in your head, when you think of air, don't think of nothing. Think of matter. Carbon dioxide. Oxygen. That's what you guys represent. And some other weird little gases out there. Xenon and radon and all these other weird gases. Okay? You guys represent the particles of air. If I have high pressure air, I'm taking you and I'm squeezing you together. The air is very dense. Don't need to do that. Okay? Get the idea? I've squeezed you together. So I have packed in a lot of air into a small space right now. So it's higher pressure there. And it will always want to go from high pressure to low pressure. If I crowded you guys all together, you'd get a little irritated. And as soon as you have a chance to escape, you'll escape. And you'll spread apart. I don't know what's in your mouth, but you need to get rid of it.
I don't have anything.
Okay, would you please sit up? Thank you. So that's the general rule. It always goes from high to low. The ball always rolls downhill. Still with me? Okay. If you understand that rule about pressure, if when I say high pressure, you picture the air particles are squeezed together very close, and when I say low pressure, you picture that they're spread apart, you've got this idea. Now let's look at a few situations and see if you can understand. Is it possible, if I were just to tie this balloon off right now, to inflate it without even touching it?
No. Yes. No.
I heard no, I heard yes. How would I do that?
Because there's already pressure inside of it, so when you tie it, you're actually pushing it more towards the.
Okay.
You're blocking off.
But I'm
the
asking, is
side,
it
so-
possible to inflate it, make it
no.
bigger?
Well, maybe, yeah.
How?
Because balloons not all together has holes in them.
Okay, well let's think about this. Little deductive reasoning. Normally we inflate a balloon by adding high pressure inside, right? Is there another way I could do it? If high pressure inside the balloon inflates it, low pressure on the outside would also inflate it. Let me show you. I'm going to inflate this balloon right here without ever touching. Are you going to be impressed?
Yes.
You should be.
Wow.
Okay, and I can keep it that way if I simply seal off the end. I inflated the balloon without ever touching it.
Wait, how does it stay like?
Pretty freaky, huh?
No. Wait.
I mean, if you look at the end of this, it's open. It's not tied off. I can look right through the bottle and I see it's open. And the balloon is staying inflated. Shauna's like, that's freaky. That's witchcraft, man. You're evil. No. How did I do that, Shauna? Tell me. All you got to do is tell me two things. There's high pressure and low pressure, right? Because remember, nothing cool happens when their pressures are the same. So I must have high pressure someplace and low pressure someplace else. Now, inside the balloon is connected to the outside of the room. So whatever pressure you have here, you're going to have inside the balloon. You understand? Because it's open. But inside the bottle is a different pressure. So my question for you is, what is the pressure inside the bottle, and what is the pressure in this room? Pressure inside the bottle is high or low? Remember the rule. Pressure always goes from high to low. If I've got high pressure, I'm going to explode, and I'm going to go towards low pressure. So where's the high pressure? In the room or in the bottle? No, I don't know. It's not going to cut it. Come on. You got a 50-50 chance. In the room or in the bottle?
In the room.
Okay. Listen to what I just said, okay? I said high pressure always wants to go towards low pressure. So think about which way the air is pushing right now. Is it pushing, is it trying to get into the bottle or out of the bottle? It's trying to get out of the bottle. How many think the air is trying to get out of the bottle? How many think the air is trying to get into the bottle? Okay, good. The thing that's keeping this balloon inflated is the air in this room. There is enough pressure in this room to keep that balloon inflated, and a lot more, too. I'll repeat, the air in this room is keeping that inflated. So that means the air wants to get in here. Why does it want to get in here? There you go. Good. In the bottle, there's less pressure than on the outside. You know how I made it low pressure. You saw me do it. I sucked out the air. Low pressure here, high pressure here. Or put another way, the air is really crowded out here. Inside the bottle, there's lots of extra space because I sucked out some of the air. Get it? You go to a beach, when it's really crowded, you'll go to the one that's not so crowded. Air is the same way. If it's really crowded out here, it's going to want to go into where it's less crowded. And that is what keeps the balloon inflated. Okay? When I take the cap off, you're going to hear a hissing sound. Is that air going into the bottle or out?
Out. In.
How many say out? How many say in? It is in. You want to spit out your gum, please. Spit it out. Anyway, it's a good thing I'm not docking people on their citizenship every time I find them with gum. We have a whole bunch of users here. It doesn't really matter. You're not supposed to be having anything. Okay? You're not supposed to have candy or breakfast. So no, what I did is I took the lid off, and the air in this room wanted to get into the bottle. And that then allowed this to be pushed back out, okay? Because it's already got a force. It wants to stretch back. It wants to return to its original shape. That's why it went down. Okay? It took a force to stretch it out.
Did you suck it in?
I went this way.
Oh, okay, so you didn't blow it.
No, I didn't blow. But I could. It would work either way. I just have to put the lid on to keep the air from moving from one place to the other. Chatoya, excuse me. Shh. Yeah, they want to get out in the case of a can of soda, yes.
If you were to blow it now that it's like that, make it bigger.
Well, yes, but now because this is trapped, it's going to be very hard. Or almost impossible for me to make it bigger, okay? Because in order for that to happen, I'd have to take the air and I'd have to compress it. That's already in this balloon, I'd have to compress it. It's going to be extremely hard. That same principle is in play here, okay? When I go to take this bag out of the pickle jar, see what happens? What? You don't see how the sides go in?
Oh, yeah.
What's causing the sides to go in? What is pushing on the sides of the bottle? The pressure where?
Inside.
Outside, in this room. The air in this room says, let me in. I want in there because it's less crowded. You see how I just made extra space? It's less crowded, the air wants to go in. I made extra space. It's less crowded in there now. The air wants to go in. You see how that's working? Now, if I poke a hole in the side, then the air could go in. And then the pressure on the outside and the inside would be the same. And this would no longer be cool. Not that it's all that cool now. It works the other way too. If I got my bag and I seal it up while it's on the outside and I try to push it in there. It doesn't want to go, okay? I'm having to compress. I'm trying to take all those particles of air like you guys and squeeze them together. And they don't like that. Now you can force it. You could force that in there. You could compress air in this jar. As soon as you poke a hole in it, it's going to come leaking out, right? Just like the air is compressed in your tires. As soon as you make a path, a hole, that air is going to want to go from high to low. Now, does all the air come out of your tire when you poke a hole in it?
No.
When does it stop leaking?
Oh. When it's at the same pressure as outside.
You got it. When the inside and the outside pressure are the same, that's when it's going to stop leaking. Now, it is possible to compress air. That's what we're doing in our tire. That's what we're doing in a scuba tank. When you get those scuba tanks that you breathe with for maybe an hour or more underwater, you breathe in and out a lot of air. That air takes up a lot more space than one of those tanks. What they do is they use a pump, and they pump regular air right into those cylinders. And they compress it so they can fit a whole bunch of air in a tiny space, just like you fit a whole bunch of air in your car tire. So that air is matter. It does take up space. And you see it here in both of those. Now, the other thing I want to show you is suction cups. Suction cups definitely demonstrate this principle of air pressure. You've got to remember that you're at the bottom of this giant sea of air. You know, when I look at my fish swimming around in the pond, I think, that's kind of freaky to be in water. That's your whole life is in water. And they're looking up at me and they're going, that's got to be kind of freaky. Your whole life at the bottom of the sea of air. How do you live in that? Well, we are in a giant ocean, okay? And I'm swimming across the room right now. And I'm pushing air out of the way. It is there. It is matter. It does take up space. And that air is pushing on me this direction, all directions. Why don't we feel it? I'll give you a hint. Taylor said it a number of times. Why don't we feel the effects of the air pushing on us, Chris?
It's the same pressure.
It's the same where?
Outside.
And inside. Yeah, the pressure inside our body and the pressure outside are pretty much the same. The only time those pressures become really different is when we breathe in and breathe out. We make what? High or low pressure in our lungs when we breathe in. I made more space. That's low pressure, guys. If I make more space in this room and we can all spread out, we're not as scrunched together, that's low pressure. Okay? When I do this, imagine all those little particles of air squeezed together. That would be high pressure, and you're going to be breathing out. Okay? It's all about a difference in pressure. But what a lot of people don't realize is that suction cups work on the same principle. When you go to the bottom of your pool and you swim to the bottom and you feel that pressure on your ears, does it matter if you're this way or upside down or sideways? Do you still feel the pressure? Yes, because you're at the bottom of an ocean. You've got to remember this is a big ocean of air. Miles of air on top of you, pushing down. Now, that little bit of air in my hand doesn't weigh very much. But the amount that's above you right now, all together, weighs a whole bunch. You don't notice it, you don't feel it, because the pressure inside and outside are the same. Equal and opposite, nothing cool happens. But if you create low pressure someplace, then the high pressure is going to want to get there. And that's when cool things happen. And that explains how suction cups work. So, you know, if you get them wet, they work better because you make a better seal. I come over here, Tyler, put Mr. Grabber on there. And I can almost lift her up. There we go. That, I think, is pretty impressive from a little suction cup. But that's because I know the science behind it. And now maybe you'll appreciate it more in the future. You know, when you stick that suction cup on there, what you're doing in slow motion, whoa, as that goes down, is you're pushing air out from underneath the cup. Okay? If there's very little air under the cup and a lot of air outside the cup, where is the low pressure? Outside the cup. Out in this room is, no, it's got the low pressure high. Inside the cup is the low pressure. Okay? Remember, air always wants to go from high to low. In this room there's high pressure and it's pushing on that cup all the way around. It's wanting to get underneath here to where there's low pressure. Head up, please. So if I make a good seal, it can't get underneath there. So the force that's keeping that on there, and that's a significant amount, is the air in this room pushing down. All you have to do is peel a corner off, and now the pressures are equal, and nothing remarkable happens. It's no longer a suction cup. Okay? So by pushing the air out from underneath, I make low pressure underneath, high pressure on the outside. And you know that suction cups don't just work going down. They work sideways. You feel the pressure in the pool, whether you're sideways or sitting up. The air is still pushing on this, sideways, okay? It'll even work upside down. This is another famous demo. You take the cup, you fill it up to the top with water. Hopefully this will work. You put the lid on top, turn it upside down, and it works just like a suction cup. High pressure in the room, low pressure outside, and hopefully, no, not going to stay on there. Hopefully the lid will stay on. There we go. Okay? The lid stays on. It's the pressure in this room holding that lid on. Head up, dummy. So you could do that on a much larger scale, by the way. You could do that with a giant container of water and a big cover, but you have to make sure that when you flip it over, you create a good seal. If it breaks at any point, it's just like the suction cup. Helica?
This person used to my classroom, and they had this thing that was like for water into, and he held golf ball to it, and he placed it in a small hole, and the golf ball stayed
actually demonstrated some other principles too that are connected to pressure. You know, pressure explains what keeps a plane up in the air. The plane's wing, based on its shape, causes air to travel at a different speed on top and on the bottom. And what that does is it creates a difference in pressure. Low pressure above, high pressure below. The high pressure below the wing pushes it up. As long as that plane's going through the air, there's pressure underneath pushing it up. As soon as it stops going forward, there's no difference any longer, down it goes. Tony?
Is that when you have the air mass and the pressure gets removed, there's no oxygen inside the plane?
I'm sorry, say that one more time.
Is that why you have the air mass? Because if the pressure is inside the plane.
Good question. You didn't hear it. She said, is that why they have air mass inside the planes? Because of the pressure. When you take a plane up and you're going at 30,000 feet, okay, that's higher than or close to the peak of Mount Everest. Now, if you've ever seen people climb Mount Everest, at that altitude, there's less air above you, so there's less pressure. And it's harder then. Every time you make more space in there, it's harder for air to go in because the difference in pressure isn't as great. Think of it this way. The more you pump up that tire with air, the more it's going to come out with a lot of force, right? We're at the bottom of the ocean, so we get a lot of force right now. But when you get up to the top of Mount Everest, the difference between the pressure that you can make inside your body and the pressure outside is very low. So when you go and you take a breath, you take a deep breath and it feels like you're not getting anything because you're not able to exchange nearly as much gas at that elevation. So if you're flying at about the same height, if it wasn't for the cabin being pressurized, you probably hear them say that, cabin has been pressurized for your comfort. Have you heard that? You haven't heard that? Wow. They say it most times. But what they do is they pump air in and the cabin is sealed off so that there's extra pressure on you. Not extra for what you have now, but what you would normally have. Because when you go up, there isn't as much pressure pushing on you. So when you are outside at 30,000 feet, whether it's in a plane or on Mount Everest, you're going to take a step and you're going to be like, if it wasn't for the pressurized planes, when you got up to go to the bathroom, Dominique, you'd go like 3 steps and you'd be like, take a couple more steps, I'm getting there. Because you have to work a lot harder. The air doesn't want to go in as much because there isn't as much of a difference in pressure. So if someone should shoot a hole through the side of your plane, the air mass drop, and you can put them on, and you get pure oxygen then. So that's going to make up for the fact that you're not getting as much air in. Yes?
What happened if one of the windows came out?
Same thing. You suddenly feel like you were traveling in Mount Everest, and of course you'd see that stuff would want to come rushing out of the plane. It probably won't suck you out like it does in the movies, but it will take anything light out right out through that hole.
So I don't really understand like how the suction cups have a lot of like, pressure, but like if it's low pressure, then how does it move in if there's like a little bit of air?
There is room. Okay? If this was not curved, if there wasn't a little pocket of air underneath there, it wouldn't work. Okay? There has to be, well, that's not really correct. Air wants to go to where there's less of it. In a vacuum, there's no air. So if you're in a spacecraft, out in space, and someone were to poke a hole in the side of that spacecraft, all the air inside that would want to be rushing out into space, because in space, there's almost a pure vacuum, a perfect vacuum, and so stuff wants to get out there and spread apart. That's the nature of gas, is that it wants to spread apart. You give it this amount of space, it'll go right to the edges. It'll be bouncing off the walls. You give it this much space, it'll be bouncing off those walls. In the vacuum of space, it'll spread out. So because there is very little air in there, and there's a lot of air here, it will want to get in there. Okay? And the more air we can pump out from underneath the cup, the better it will stick. But as soon as we create a gap and the seal's broken, then the pressures are equal and nothing happens. Okay, I want to show you this. We're kind of a little bit behind now. So you look at this balloon. It's in a vacuum chamber, but nothing has been turned on yet. So the pressure outside and inside are equal. Predict. No class has gotten this right 100% so far today. Let's see if you guys can. Predict what's going to happen when I turn on the vacuum pump and I suck the air out from inside this container. Will the balloon get bigger or smaller? All those that say bigger, raise your hand. All those that say smaller. So much for getting 100%. I was hoping I would convince you guys. Remember, you're just like this balloon. You have some air in you, right? But right now, the pressure in this room is keeping you down. It's pushing you down. It's pushing in all directions. You're used to that. That's the pressure you normally have. But if I were to remove the pressure that's pushing on you, you would expand. If I were to take you and kick you out of my spacecraft and put you in a place where there is little to no air, your tissues would expand. Your your cells would rupture. You would bleed internally, and you would die very quickly. You'd be kind of puffy looking too. Okay? So that's what would happen to you in space. I didn't add more air to the balloon. The balloon is tied off. So it's not possible to add more air. What I did is I took that invisible hand of atmosphere that's holding that balloon down, and I took it away. So now the balloon can stretch out more. Ruben. I can't, because it's sealed on there. I couldn't pull it off. But if I did, as soon as I broke that gap, it would have done the same thing you saw there, and air would have gone rushing in. Because it always goes from what to what? High to low. It's high in here, low inside. Victoria?
Is that why, like, people that are deaf get swollen? Because there's no air and then, like, plus the blood?
Actually, one of the big reasons people swell, because you didn't really change pressures when you died. The reason people swell when they die is because of decomposition. Your tissues decompose and they release gases, and it's basically the bacteria releasing gases that cause your tissues to swell. Okay.
What are those?
Marshmallows.
Yay!
And again, people get confused when they see this. They think that the marshmallows are expanding because I'm adding air to them. No, I'm not. Head up, Chris.
You're growing marshmallows.
I'm not adding air. In fact, I'm taking air away. That air that's keeping that marshmallow small, I'm taking it away and allowing it to stretch its legs. Now, because of the little snapback effect, when I take and turn that off and the air goes back in, they're actually going to get smaller than they were to begin with. Because they're kind of
Can I
snap
see
back.
how you're doing that? I want to get close.
Now you get cute little...
Can I have one?
No. Okay? Alright, I have one more demo I want to show you, and then we got to get to this lab, because we are way behind. I love your questions, guys, and I wish we had 2 hours, because I would be happy to answer them all. But this is the last one. Okay, so most of you were wrong on that one. Taking the pressure away from it made it bigger. Here's kind of the opposite. This is what would happen if I suddenly removed all the air from within your body. The air inside your body, the pressure inside your body is pushing against the outside pressure. And that's keeping you from getting crushed. But if I suddenly remove the pressure from inside your body, which is what I'm going to do here, no, it's not going to be a loud bang, don't worry. If I suddenly remove the pressure from inside your body, it would be the same as you diving to the bottom of the ocean without a sub. All the pressure, all the weight of that water would be pushing on you. And you wouldn't have anything to push back. Here we go. 1, 2, 3. Okay? That can was crushed by the air in this room. There's enough force to smush you down pretty good by the air in this room alone. Okay? And if that's not impressive to you, that same demonstration can be done with a 50-gallon oil barrel, like the kind we have for trash cans out there.
Is it loud?
I don't remember being too loud, but the can does crush. Just from the air in this room, there's enough pressure. So whenever you have high and low pressure, the high pressure always goes to the low pressure. It's trying to equalize, okay? So that explains the breathing part. Now, what we're going to do with this lab is measure our lung capacity. And I'm going to show you the way the doctors do it, and then I'll show you how we're going to do it. And guys, I kind of have to move you fast now because we started this a little late. All right, what I'd like you to do is go ahead and flip to the back of this, and you'll see a table. That's this table right here. And it describes, or it shows a number of different, put the ruler down right now, okay? Shows a number of different measurements that we take of someone's lung capacity. Some of you might have seen something like this before. Maybe you went to the doctor for asthma, or maybe you had an operation and they had you use one of these. Basically, you breathe in and you try to keep that little thing between the arrows. And you see how high up you can get it before you run out of air. So I made it to 2,500. I win. 2,500 milliliters. How many liters is that? Head up, please. 2,500 milliliters. How many liters is that? 2.5 liters. You know what a 2-liter bottle is like? So it's 2 liters plus half a liter more. That's the volume of my lungs, okay, roughly. Well, I'm now going to do that measurement a different way. I'm going to do it using a balloon. I'm going to capture the air in 3 different ways, or 3 different measurements of that air capacity. This first one is called your vital capacity. Vital means life. And this is all of the air. This is the maximum amount of air you have in your lungs. You might even want to write that below that column, so when you do this on the way, you remember it. Maximum amount of air. So for this one, I'm going to start by stretching my balloon. Okay, you are not to make little eep squeaking sounds with the balloon. If you pop it or break it because you're fooling around, you'll have to come up with your own. I'm not giving you another one, okay? But you'll take in your full breath. And you blow out every last bit, okay? Do not continue to breathe in through your nose. That would be cheating, okay? That is my vital capacity. Now, in order to figure out how much air is in this sphere, I'm going to use a formula. You can see the formula there at the top under number 9 on your sheet. It is volume equals 1.33 pi r cubed. Okay? There's no diameter in there. I'm going to find the diameter and then use that to find the radius. What is the radius? Yeah, from the center out. So how does that compare to the diameter? It's half the diameter, exactly. So show me the side of the ruler. Show me the side of the ruler you're going to use for measuring. Hold it so it's facing me. So I know you know which side you're going to use for measuring. Hold it so it's facing me. No, 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 no. Those of you that are showing me the side with the safety ruler written on it, that is not the side you're going to use for measuring. That's not the metric side. You're using this side. The side with all the little teeny tiny writing on it, okay? So make sure you're using the sides with the centimeters. One edge has the tiny lines and one has the bigger lines. The tiny lines are what? Millimeters. We're not going to be that precise with this. We're going to measure to the nearest half centimeter. Taylor, I don't want to send you out, okay? So you're going to hold the balloon with the opening to the side like this on your desk, and you're going to measure. Okay, you're about done. You're going to measure the diameter. To do that, notice that 0 does not begin at the very end. It's about a centimeter up. So if you do this, you just measured a centimeter too much. Got it? So you can have it overhang the edge a little bit and do it like this. Mine comes out to be 20. Or you can just go, oh, it says, actually a centimeter too little. That's what I meant to say. Or you can look at it like this and it says 19, but I know that's really supposed to be 20. Okay? I don't care, but just remember that that is not where 0 is. 0 is a centimeter up. If you want to do it on the side of your desk here, that's fine. But don't try to do it like this in your lap. You write down that measurement. In my case, it was 20. And then you repeat the test how many more times? 3 more times. So I write down my other numbers, and I get my total, and then I find my average. To get the average, it's the total divided by 4. The answer goes here, okay? Once you have the average diameter, then you can calculate the volume. Notice there is no label. You need to make sure you put the label. If you even want to write the CMs in right now, that's fine. But you got to put the label on all of those. Okay? There's no label, it's going to be wrong. Now to do the calculations, let me walk you through this first. You refer back up here. We get our average diameter. It's going to come out to be 20 on mine. Okay? 20 centimeters. To find the volume, I need to find what the radius is first. The radius is 1/2 the diameter, so that'll make it what? 10. And it says I'm supposed to take the radius and cube it. Radius cubed means what do we do with this number? Multiply it by, no, not by 3, by itself 3 times. That's what 10 cubed means. That's what radius cubed means. It's the radius times itself 3 times. Then I need to multiply it by pi, which is 3.14. Then I need to multiply it by 1.33. And that is going to be my answer. You can round it off to the tenths place, and that is going to be your answer. You can refer back to this at home if you get stuck. What you need to get done today is this part. Monday you'll turn this into me with all your final calculations, but you need to get this part done, okay? Also, don't forget the crossword puzzle and the quiz for our next class as well. All right, so let me show you what the remaining 2 are. You still have a question, Ruben?
Yeah. By the total,
Add them up. That's generally how that's done, yeah. Okay, expiratory reserve is the next one. And that expire means to breathe in or out? Out. Reserve means, yeah, save, leftover, the part you save inside. So you breathe in and you breathe out, and there's still a little bit left in there, okay? And that's what you're going to blow into the balloon. So you breathe in normally, out normally, and then you capture the leftover. It's not going to be very much. Same thing. Find the volume. Find the diameter, half the diameter, then multiply that by itself 3 times 3.14, and times 1.33. After you find this number, okay, you got to get this first. Tidal volume, so the expiratory reserve is what we would refer to as the leftover. And then the last one here, the tidal volume, the tide comes in, tide goes out. That's your normal breathing, in and out. So you just breathe in normally, out normally, whatever that is. It should be more than the leftover. Your normal breath should be more than the leftover. The biggest one should be the vital capacity. Everybody got it? As soon as you get your balloon, get your 12 measurements done, and you can finish the rest at home.